Hello again. Today we start next lecture on digital design course, Introduction to Boolean Algebra. Boolean algebra or logic algebra is a branch of computer science and mathematics used to manipulate and process binary information. It was founded by the English scientist George Boole, who wrote a book in 1853, Investigation the Rules of Thought, and founded the theory of Boolean algebra. Any Boolean variable can be in one of two states, 0, 1, true, false, high, low, etc. And this is make it very useful for designing digital and electronic hardware components. A Boolean function consists of one or more Boolean operations and produces a single output value from a set of other Boolean input values. All the input and output values can be only 1 and 0. There are three basic logic operations. Basic logic or Boolean operations, and or not. We start with and. The symbol for and is like that, or dot, and in the course we just, for example, A and B will write in this way. And for or, the symbol is like that. During the course we are going to use the plus sign, but here it's an logical addition, not arithmetic. And for the not, the symbols are like that, or even, for example, not X in this way, or not X in this way. In the AND operation, all inputs need to be 1 to set the output 1. Otherwise, the output is 0. And if we have two variables, x, y, the truth table for the AND. In the truth table, we list all the states of the variables. Since we have two variables, then we have 4 states. For n variables, we have 2 to the power n states. Here, n variables, number of states, 2 to the power n states. For example, for a 3 variable and we need to state 8 states, and here x and y, the value of the function for each state. By definition, x and y, if 0, 0, 0, 1, 0, 0, 1, 0, and 0, 1, 0, and only 1, 1, 1. So x and y is equals to 1 only if both the variables are, or the inputs are 1. In the same manner, if we have 3 variables, x, y, z, you list all the states, etc. 1, 1, 1, x and y and z is 0 in all these cases, and 1 only here if all the inputs are 1. The graphic symbol for the AND logic gate is like that. Here x, y, x, and y. X and Y. So the output is 1 only if both the inputs are 1. Otherwise, the output from the gate is 0. To illustrate the function or how it works, we can use the following electrical circuit with 2 switches connected serially, and suppose we have here a lamp, this switch X, switch Y. As you can see, the lamp will light only if both the switches X and Y are 1. If any of them or both are off, then the switch will not light. This is not the electronic implementation of the AND gate. The electronic implementation using transistors and other electronic components is the subject of digital electronic course. This is illustration how AND gate works. Next we move to the OR gate, OR operation, OR. In the OR, if any of the inputs X and Y, truth table, if any of X and Y, anyone is 1, then the output is 1, X or Y, X or Y. And it is 0 only if all the inputs are 0. And in the same manner, you can obtain the truth table if we have 3 variables. The graphic symbol for the OR gate, here we have X or Y. X or Y will be 1, the output, if any of the inputs or both are 1. Otherwise, it will be 0. And again, we can demonstrate the work of the OR by means of the following electrical circuit. If we have the 2 switches but connected, and here we have the lamp, switch X, switch Y. As you see, if any of the switches, if any of the switches X and Y or both are on, then the lamp will light, and it will not light if both the switches are off. This is the OR operation. And next, the last basic logical operation is the NOT. Here we have only 2 states, not X, if X equals to 0, not X1, and here 0. Do you see? And NOT is a uni-operand operation, while and OR are at least 2 operand operation, not uni-operand operation. And the graphic symbol for the NOT gate, here X, not X. So it just complements the input. If the input is 0, then the output is 1, and if the input is 1, the output is 0. These are the basic logic operations, and or not. Any Boolean function can be expressed using these three basic operations. And any logic circuit can be drawn using these three logic gates. Logic gates. Before moving to the laws of Boolean algebra, from the definition, we can note that if we have the variable x and it with 0, then the result always will be 0. X and it with x always will be x. Since if x is 1, 1 and 1, 1, if 0, 0 and 0, 0. And x ORed with x, always x. If x1, then 1 or 1, 1. If x0, 0 or 0, 0. X ORed with 1, always 1. Since anything ORed with 1 is 1. X ORed with 0, always x. If x is 1, then 1 or 0, 1. If x 0, 0 or 0, 0. X ANDed with not x, always 0. Do you see here? We will have this component or this 0, so the output is 0. But x ORed with not x, always 1. Since again, one of these will be 1, and 1 ORed with anything is always equals to 1. X, this is called the double negation rule, complemented twice, always equals x. Laws of Boolean algebra. These are the laws of Boolean algebra. We are going to prove some of these laws by means of truth table or Venn diagram. This is the AND form. And this is the OR form. Commutative law, A and B equals B and A. So X and Y equals Y and X. And for the OR form, A or B equals to B or A. Associate law, A and B together and C equals A and together B and C. And for the OR form, A or B together or C equals to A or B or C together. Distributive law, A or B together or C equals to A or C and B or C. A or B for the OR form and C equals A and C or B and C. Identity law, A ANDed with 1, I already told you about that, equals always to A ORed with 0 equals to A. 0 and 1 law, A ANDed with 0 equals 0, A ORed with 1 equals 1. Inverse law, A and not A equals always to 0, and A or not A always equals to 1. Idempotent law, A and A equals to A, A or A equals to A. Absorption law, A and A or B equals to A, and the OR form A or AB equals to A. We have two important laws, De Morgan's laws. A and B all complement equals not A or not B, and the second law, A or B all not equals not A or not B. And double complement or double negation law, not X complement, not X twice, or X twice equals to X. Next, to prove some of the laws, for example, A or AB. This is equals, we know this is A, but why A ended with 1 or B. 1 or B equals to 1 always, so A and 1 always equals to A. We can use this rule if we have, for example, A or A not B, C, or A, B, not X, etc. Since we have A alone here and repeated in other terms, then the result is again equals A. Now, A or not AB. Before writing, I will obtain the truth table. Not A equals to 1, 1, 0, 0. And not A ended with B equals to 0, 1, 0, 0, 0. Ored with A, this bad. A or not AB, 0 or 0, 0, 0 or 1, 1, 1 or 0, 1, 1 or 1, 1. Do you see? You know that this is equals A or B. Next, for example, if we have A or B, A or C. This is equals to, now A and A is A or A and C, or B and A or A and B, or B and C, which is equals to, these together are A. So we have A or B, C. A or B, C. Next, we move to De Morgan's theorems. A and B or not equals to not A or not B. Sometimes it's good to write it in this way, and B equals not A or not B or not. The same form. To prove it, for example, by means of truth table, A, B, we list the 4 states, A and B, 0, 0, 0, 1, and A and B or not 1, 1, 1, 0. This is the left side. Now, not A, 1, 1, 0, 0, not B, 1, 0, 1, 0. If we OR these together, not A or not B, then we have 1, 1 or 0, 1, 0 or 1, 1, 0 or 0, 0. So do you see? This is the same as here. They are the same. So this is proved by means of truth table for the first De Morgan theorem. As an exercise, please prove it for 3 variables, A, B, C equals not A or not B or not C. Do you see in the truth table, in this case, we have to list the 8 states from 0, 0, 0 to 1, 1, 1. Find the left side and the right side and see if they are equal. In the same manner, we can prove De Morgan's second law, which is A or B or not equals to not A and not B. Or we can sometimes write it in this form. They are the same, not A and not B or not. Again, by means of truth table, we list all the states 0, 0, 0, 1, 1, 0, 1, 1, A or B. Now the left side is equals to 0, 1, 1, 1, 1, and we complement it. So now this is 1, the left side. The left side. Now the right side, not A, equals to 1, 1, 0, 0, and not B equals to 1, 0, 1, 0. Now if we add them together, not A and not B, we have 1, 0, 0, 0, which is the same as here. We can prove De Morgan's law, for example, A and B or not equals not A or not B by means of Venn diagram. Here we have A and here we have B. A and B is this part. I'll color it. This is A and B. The complement of it is this part, the green. Which is the green part, A and B or not. Now, we have another circuit, AB. This part is not A. This is not A. And this part is not B. Not B. If we OR them, we obtain the same here as in the green. you can prove for three variables using Venn diagrams for four variables or more will be difficult, and we will learn more methods to deal with logic functions if we have more variables. Next, simplification of Boolean expressions using Boolean laws of Boolean algebra. For example, if we have A or not A, B, we already know that this is equals A or B. We proved that. Do you see this is the circuit here before simplification? Here A or not A, B. And here just A or B, the same. So simplification is useful since we reduce the complexity of the circuit, we reduce the space, heat, cost, power consumption, etc. We'll use laws of Boolean algebra to simplify Boolean functions, and later we'll learn how to simplify using K-maps and the QM method. Now, about this, I already wrote that not A or A. We can use the same. We can assume that A equals not X. So this one will be X or not XB. And this one is equals X or B. So again, we write X equals not A or B. If we have this one, I already wrote that it is equals to A or AC or AB or BC, which is equals to A or BC. Do you see this part? Is the circuit before simplification, and this part after simplification, A or BC. Sometimes you need to calculate the cost of the circuit. There are several ways to calculate the cost. One of them is to sum the number of gates plus number of wires. So in the first case, the cost is we have 1, 2, 3 gates, plus, and we have 1, 2, 3, 4, 5, 6 wires. So the cost is 9. But in the second case, we have 2 gates plus, and we have 4 wires. So the cost is 6, while the cost here is 9. So using the form after simplification is better. Next, suppose we have the following function, xy, or ANDed with x. This is equals to x and xx, xy, or xy and y, again xy, so this is equals to xy. Regarding this, x and x is x, or x not y, or xy or y and do not y is 0. X or, do you see this differs in one variable, y, so this is x. Since x not y or xy equals to x not y or y, and this is 1, so this is x. X or x again equals to x. Here you see directly that xz ended with not y or y again equals to xz. If you have any two terms, or, and they include the same variables and they differ on the state of one variable, then you can remove that variable. For example, A, not B, C, not D, or with A, not B, not C, not D. You see these two terms differ on the state of C only. Here we have A, not B, not D. So we can simplify it A to the A, not B, not D, directly. Next, we have the following example. F equals not X, I will write it, X, Y, Z, or XY, not Z. Again, these two terms differ on Z, so they are equal XY. And we already know not X or XY equals to not X or Y. For example, if we have this one, not A or not B or not, or not AB. Using De Morgan's law, this is equals not A twice and not B twice, or not AB, which is equals A and B, or not A, B, and again this is equals to B. For example, in this you have C ended with A not B, ended with C or BD, or with not A not B. We can first deal with the internal bracket, which is equals A not B, C, or here not B and B, 0, 0. Or with not A, not B, and this is multiplied by C, equals to A, not B, C, or not A, not B, C. And this differs on A, so this is equals to not B, C. This is the function in its minimal form. Minimal form means that we cannot simplify the function furthermore. For this lecture, thank you. We will move next to the secondary logic gates.